Right, so our first speaker today is Neil Strickland from the University of Sheffield, who's going to tell us about lean in new research.
Okay, thanks. That's a bit loud. Okay, so the plan is I'm going to talk a little bit about using lean actually as a tool for doing new research. I mean, I guess most of the activity that people talk about is just formalizing stuff that's been known for a long time. But here I'm going to be talking about this paper, Iterated chromatic localisation, that me and my student Nicola Bellumat, we just wrote last year, and we formalised part of it. So I'll talk a little bit about the actual content of this project. So I'll show you also. Here we go. Here's the actual paper. Fairly conventional sort of paper in algebraic topology, stable concept theory, but you see at the end of the abstract, combinatorial parts of this work have been formalized in lean. Okay, so I'll talk a bit about the actual content of this, but I mean it's not anything especially exciting just from the point of view of formalization. It's a fairly routine sort of thing, while the nowhere near kind of really the state of the art of formalizing complicated mathematics. But I'd also like to talk a bit more about just about infrastructure and ecosystem. I mean, I guess it is kind of part of the vision that this kind of thing might be routine. That lots of people might be writing their papers, and they would decide to formalize at least the parts that are conveniently accessible for formalization, and then that would make the job of the referees and the readers a bit easier, and it would make sure that we didn't have mistakes, at least in those parts. But lots of people are writing papers. So I just checked that there's about 35,000 papers on the archive in mathematics this year, and about the same in computer science. So if even a tiny fraction of these people start formalizing stuff, then that kind of changes the numbers on what's happening with lean or with coq in a really rather striking way. So some things we should talk about. Well, this we want to try and minimize the learning curve for everyone involved, for the authors and for the referees and the readers and so on. That's various things can be done about that. But also just kind of new conventions about where everything goes. I mean, now we've got very effective conventions nowadays about what happens with papers in mathematics. I mean, but essentially everything goes on the archive, and got a good infrastructure of people getting notifications from the archive about papers they're interested in, and the archive is very nicely set up to deal with any kind of LaTeX that you might possibly want to use, and that's all great. So if formalization were to become routine, then you would need same kinds of infrastructure. So one part of that is just where and how you store the lean code. One aspect of it is that if you're going to have like an immutable version of the PDF, then that should, and you're going to have a formalization, then that should also kind of be immutable, and you should have a clear snapshot at the time of publication. But what's typically going to happen, of course, is that the author's going to want to develop further what they've already done, and so that creates a bunch of issues about version management and so on. And then also there's a bunch of issues to ask about what's going to be the relationship between MathLib or central libraries of some kind and individual developments for individual papers. You want to, I mean, if you look at the Isabelle ecosystem, they seem to have got this working quite nicely, that they have this archive of formal proofs. People submit stuff to the archive of formal proofs, and whenever Isabelle gets developed further, people add stuff to the standard library. It's kind of awesome. The whole of the archive of formal proofs gets built again, and you check if anything breaks. And if anything breaks, then whoever, I believe the story is that whoever makes the change to the standard library has the responsibility of fixing anything in the archive in formal proofs that they've broken. So there's that kind of issue that we want to address in the lean ecosystem, and also just the issues of when and how developments that start outside MathLib should migrate into it. Another issue is that what's the model of the interaction between sort of the LaTeX code, the PDF file, and the formalization. I mean, various different models are possible depending on how tight the link is between the two versions. I mean, for some things where it's feasible to formalize the entire content of the paper, then it might be natural to have some kind of very tight integration, have some kind of literate lean type thing where the lean code and the LaTeX code are all in the same file, and it gets processed in some way. But for this particular project that I'm talking about, we have much looser coupling. I just wrote the paper in a kind of a conventional mathematics style, and then wrote the formalization separately. And but then you can at least hope for some kind of annotation between the two. Between the LaTeX and the lean code to just try and keep things in sync. But and sometimes the whole structure will be very parallel, but it's also kind of, I think, quite common that when you come to formalize something, you just really need to do it in a different order from the order that you would naturally write for a human reader. So, and some things which would be very small in the LaTeX file become quite big in the lean, or vice versa. And also, there's a whole bunch of issues about what happens if you want to formalize some part. You want to find your new contribution to the literature, but you want to do it sort of modulo stuff that's been done already. You're not going to reformalize all the stuff that you're relying on. You just want to quote it. But if you're doing that, then there's a bunch of kind of information management challenges associated to that. You need conventions about how you're going to refer to stuff that's already in the literature, and how you're going to formalize the statement of it, even if you're not formalizing the proof. And there's a bunch of issues that are likely to come up if people start doing this sort of thing on a large scale. That you're going to have different people who are going to try and do and formalize the results of the same paper, because they want to quote it, and they'll do it in different ways, and then there can be a bunch of nightmares associated with that. But anyway, so let's just have a look at this paper that I'm talking about. So what's in it? So part of it is general homotopy theory and category theory of finite partially ordered sets. Okay. Finite partially ordered set, that's fairly simple combinatorial structure. And we're doing everything. Everything has decidable equality, so we're not decidable. The orders are all decidable as well. So everything's as discrete as possible. But then, there is this homotopy theory. I mean, maybe people aren't necessarily so familiar with that. But you can do that. If you've got a finite partially ordered set, you can make a simplicial complex out of it, where the points of the partially ordered set are the vertices. And you say that a subset is a simplex if and only if it's totally ordered with respect to the partial order. And so that gives you a simplicial complex, and from the simplicial complex you create a topological space. And then you can, so you know what you mean by homotopy theory in topological spaces, and there's a whole kind of parallel structure of definitions, homotopy theory in partially ordered sets. And it turns out that if you set things up the right way, I mean, the homotopy theory of finite partially ordered sets is the same as the homotopy theory of finite simplicial complexes, or finite CW complexes. So that's kind of a nice picture. But we actually, so here in this paper, we don't actually set up any, we don't prove anything about the relationship with ordinary topological homotopy, but we do set up the homotopy theory for finite posets. And then we introduce a bunch of rather specific finite posets that will come up on a later slide, and define various maps between them and prove various homotopical properties of these partially ordered sets and maps that kind of feed into the rest of the paper. What's in the rest of the paper? Well, there's a bunch of stuff about derivators. So what's a derivator? Kind of the sort of central motivating example is like this. If you've got a finite partially ordered set P, then you can look at P-shaped diagrams of topological spaces. So for every element of the partially ordered set, you've got a topological space. And whenever you've got a comparable pair, P less than or equal to Q, then you get a map from XP to XQ, and they compose in the usual way. That's what I mean by a P-shaped diagram. And then there's a homotopy theory of P-shaped diagrams, a homotopy category. And so we've got this kind of this construction which sends a finite poset P to the homotopy category of P-shaped diagrams. And now that's a kind of strict two-functor from posets to categories, which satisfies various properties, and derivator is is a thing like that, which with subject to some axioms that are motivated by this example. So there's a bunch of stuff about derivators in the paper, and then there's one particular example of a derivator is a derivator where you get the category associated to a finite partially ordered set is the homotopy theory of P-shaped diagrams of spectra in the sense of stable homotopy theory. And in that case, there's a bunch of, there's this whole massive story about chromatic homotopy theory, huge literature about that, and some parts of that we have to, they come into this paper. Yeah. So what is formalization status here? Okay, so point A, this general homotopy theory and category theory of finite posets, so that is completely formalized. Not formalized in the kind of the optimal way, because we didn't use the category theory from method. At some point, we should translate that so that we do use the method category theory, but just something we haven't got around to doing yet. Yeah, and then these particular finite partially ordered sets, I mean, that's the main point. That's the main work that we did, was to formalize that. Then there's C theory of stable derivators, which we didn't make no attempt to formalize at all, but it's worth making a few comments about what's the status of that. I mean, so there is this category theory library, which seems to be usable for various things. I still haven't really got to grips with it, so I've not really used the category theory library to do anything very much. I kind of had a bit of a look at it, but then you would need to go kind of beyond that. I mean, in some sense, halfway between categories and derivators is the theory, or stable derivators, it's the theory of triangulated categories. So I believe, I don't know of anyone working on triangulated categories in MATLAB yet, or in Lean. But I would say that it's kind of similar complexity to abelian categories. Abelian categories, to the best of my knowledge, I mean, there's in Scott Morrison's category theory library, there are some stubs about abelian categories. And I don't know whether that's because it's kind of really difficult, or whether it's just standard normal deal about priorities and time. But anyway, so I don't really know how hard that would be. But then, then the natural language for dealing with derivators, though, you would need at least strict two categories and maybe bicategories. Well, certainly for some things you need bicategories. Some things where you get away with strict two categories. So how hard those things would be, again, that's you'd have to try it and see. Well, for part D, to do any chromatic homotopy theory, I mean, that would be kind of a huge, massive project to formalize anything to do with chromatic homotopy theory. So I think that's kind of really in sight. But there is kind of at least a sort of nice clean API, as it were, between C and D. Right? I mean, there's you do A, B, and C. You prove some stuff which is valid in any stable derivator with some list of objects with certain properties, and that's what kind of you could set all that up. And then the point about the chromatic homotopy theory would just be to say that in the stable homotopy category of spectra there exists here's an example of that axiom system, and so it is kind of cleanly separated. So just to give a bit of a flavour, I'll talk a little bit through what are these combinatorial objects that we're talking about. P is subsets of fin N, Q subsets of P that are closed upwards. Okay. So these, of course, are just these are finite partially ordered sets in an obvious way. So actually not quite such an obvious way, because Q you're supposed to order by reverse inclusion. I forgot to say that. And then we have this predicate A angle B. That means that every element of A is less than or equal to every element of B, which is not an order. Note that vacuously the empty set angle B and A angle empty set are always true. So that kind of breaks things that you might expect. Then we have this map mu. You've got two of these upward closed families of subsets, U and V. And then, oh, yeah, typo there, I should say U star V in the middle, not A star B. So U star V is the set of unions, A union B, where A is in U, B is in V, and this angle relation is satisfied between A and B. And you check that this makes Q into a non-commutative semi-ring, this operation. And then, so we have this, like I said, this homotopy theory of finite partially ordered sets. There's kind of a strong version and the weak version. And so strongly contractible, what does that mean? It means you've got a family of maps Fi from P to itself, which kind of go, they form a zigzag, F0 less than F1, greater than F2, less than F3, etc. And then eventually you get to some constant thing. So if you can join the identity to a constant map by a zigzag like that, then we say that your P is strongly contractible. Then you have an arbitrary map of finite posets from P to Q. Then you have these so-called slice posets or comma posets. F slash Q is the set of P, such that F of P is less than or equal to Q. And you want to ask whether that's strongly contractible in the sense of the previous point. And we say that F is homotopy final if that's valid. And then we can do this U box times V, that's a set of pairs A, B, where A is in U, B is in B, and angle relation satisfied. So by definition, mu UV is the set of A union B for A, B of that form. And yeah, so you get a union map from this box times thing to the U star V thing. And it turns out it's both homotopy final in the sense of previous definition and homotopy cofinal, which is the dual thing. So it has both those properties. And that turns out to be kind of, that's sort of the key point in the, that's sort of the end of the formalization, really. There's a big story about what this is good for and how this feeds into the whole thing about iterated chromatic localization, which is what's supposed to be the actual point of the paper, but in terms of the combinatorial homotopy, that's the punchline. So yeah, I mean, I'm sure you can all see that this is the kind of thing that it's pretty amenable to this sort of formalization. And it's the kind of thing also where it's easy to get the edge cases wrong. It's easy to mistakenly write an inequality the wrong way around at some crucial point. Yeah, it's good to formalize. Let's just have a quick look at what do we get in the lean code for this. Well, so we've got about 240 lines of stuff about fin n. Again, so there's some of this tiny lemmas that could be in the MATLAB. Then also just got a non-empty subset of fin n obviously has a largest and smallest element, subject to decidability conditions. That's not quite in MATLAB, so we need a bit of work on that. Another thing that I think probably should be in MATLAB but currently isn't, if you've got a finite decidable type, size n, then there's a unique order-preserving bijection from it to fin n. Several slightly different closely related incarnations of that, so need some work to do that. Then, as I mentioned, there's this sort of category theory, strong homotopy theory, finite partially ordered sets, 500 or so lines of that. This is operation of subdivision of finite partially ordered sets. So in this situation, what does subdivision mean? You've got a finite poset P, you look at the non-empty chains in P. A chain is just a subset that's totally ordered. Then you look at the non-empty chains, that's itself a partially ordered set just under inclusion. Turns out that the geometric realization, the topological space that you get from that subdivision is homomorphic to the geometric realization of your original P. And, but it turns out, yeah, for a kind of slightly non-obvious technical reason, that doesn't interact in the most obvious sort of way with the strong homotopy theory, so you have to do some work to deal with that. Yeah, and then so that actually points to A to E. That's about 2,000 lines, and then there's another 2,000 or so lines that are about these specific partially ordered sets and maps between them that I mentioned. And just for comparison, right? So that's about 4,000 lines of lean corresponding, whereas the paper's about 3,500 lines of LaTeX, 42 pages of PDF. But actually, it's kind of a bit arbitrary how you count, but you could say that roughly 7 pages are fully formalized in that. Okay, so what do we do with the lean code? That's another question. Okay, so so what I did in the first instance is, like I say, I think it's sort of one ought to have a snapshot that's kind of tied with the original submission or acceptance of the paper. So what I did was to put ancillary files on the archive. It's not something that people do that often, but there is this facility on the archive that you can submit ancillary files that get tied to your paper.
Really, one gazette file?
I think, if I remember rightly, that if you submit a zip file, then the archive unzips it, but it also offers you to zip it if you want to download it. So then, so I mean, certainly this option is not very satisfactory in the way that I did it, and I didn't. I didn't actually attach any instructions as to what you're supposed to do with these files. You could spend quite a long time setting up a detailed set of instructions that anyone should follow, and I didn't tie it actually to a particular version of lean. I mean, what I should have done, I guess, is to upload leanpackage.toml as another ancillary file, but I didn't do that. But anyway, the archive is not really terribly well set up for this. It's not a hugely convenient way to deal with things. But so, yeah, we also have a GitHub repository that's specific to this paper. And there's kind of a little bit of an issue about what will you do with this as well. I mean, so I made just a separate repository for this, which I guess is something you can do. But of course, and I think that for this particular paper is kind of a little bit isolated, and maybe that's kind of okay. But other kinds of things you might do would be very natural. You'd have a whole series of papers about related things, and then you'd want to have a single repository in which everything kind of builds up. And then, so it's not quite clear what's sort of the best way to handle that. Then again, so I submitted this paper, 5 or 6 months ago, and then I actually kind of more or less stopped doing lean stuff for a while after that because I was working on other projects. And during that time, of course, the code rotted against the current mathlib. So yeah, you might have to kind of think a little bit about how to manage that. And I think in some sense that is a solved problem. It's just that I don't really, I'm not really sufficiently familiar with the solution. I mean, I think if you did the right thing with leanpackage.toml and elan and those kinds of stuff, and and linking to specific commits in the Git repository, then you should be able to set things up so that the referee could follow some link that you've obviously given them and get themselves the right environment in which the code is not broken. But I think there's more thought needs to go into exactly what to do with that. That's more or less what it says there. Another group of things to think about is, how are we going to cross-reference between between LaTeX and Lean. Yeah, so what I did here is just a rather kind of crude initial thing. You just in the Lean file, I put these comments like this. Because you don't really want to cross-reference to actual theorem numbers in the LaTeX, because those are going to change if you edit the LaTeX file. So you can cross-reference the LaTeX labels. Then, of course, if anyone wants to know what they mean, you have to actually look at the LaTeX source, or you have to compile the LaTeX source with some style file that shows you the labels, or do something else like that, or set up, like I say here, you could, certainly one could set up some kind of post-processing script that would go through the Lean file and automatically attach theorem numbers to these labels. But yeah, and and in thinking about what's the right infrastructure for this, like I say, you should bear in mind that the correspondences can often be quite ragged. There's a bunch of things that you do in bunch of things that appear in the paper that are kind of just obvious to a human, and but then they actually take some substantial number of lines in Lean, and so you can't really have a kind of fine-grained correspondence there, and some things in the opposite direction. Then one should think about how to move stuff into MATLAB. I mean. So there's a bunch of stuff that I did, which like I say, could be in MATLAB. And I think the fact that I did it is kind of is good evidence that those results are needed. But quite often, of course, I mean, I might not have done them in the best possible way, and more expert people would think that some different approach to getting to roughly the same point would be better. So although the fact that I did it is evidence that it's needed, that doesn't necessarily mean that my code should just go into MATLAB, but somehow it would be desirable to have that functionality in MATLAB in some way. But I think we do run into the fact that I think getting stuff into MATLAB is somewhat slow at the moment. You can put in PRs, and I mean, I'm not complaining about it, but here's an observation that we don't have that much manpower to review PRs, and if stuff's complicated, then it takes time to get reviewed and to get revised in response to people's comments. Yeah, as I mentioned before, these are the numbers, 35,000 math papers a year, and so even 1% of those math papers come with formalizations, and that creates kind of a lot of stuff to get digested. So there was this MATLAB nursery, which I'd kind of forgotten about. Then when I was preparing this talk, I sort of decided to look again at MATLAB nursery, and maybe that's kind of part of the solution, to have more of a systematic use of MATLAB nursery as a sort of staging point for developments of this kind. But it does seem, like I said, at the moment, that's just not happening. There's I think there have been very few commits to MATLAB nursery within the last year or something. So like I say, I would say about half of the stuff that's in this project is stuff that could very plausibly just go into MATLAB in some very similar similar form to what we've got at the moment. But then half of it is really kind of rather specific to this particular development. So we can have a discussion about what should happen with developments of that kind. Because if it doesn't go into MATLAB, then it will what. And so maybe one part of the solution to that, you could imagine sort of setting up Travis to sort of try and build the outside external repository, but to build it against the current version of MATLAB and to report as things rot. Yeah, so I kind of have thought about doing that, but I haven't learnt enough about Travis to be able to set it up. So, and we don't. I think at the moment the method documentation has no. I think it doesn't mention Travis at all. Doesn't give me any instructions how one might proceed with that. So. Yeah, the other issue that I mentioned about referring to the literature. So again, this is not something that's actually a live issue with this particular project because the stuff that we formalized is just self-standing. But if we decided to formalize any more of the paper, then we would have hit this issue. Just by way of example, what's the kind of key player in all this? Boardman's stable commutative category B, and there's this complex cobordism spectrum mu. It's an object of B. So suppose we just take this as an example. I mean, suppose we're not willing to try and formalize the definition of B or mu, but we want to refer to them and quote some stuff from the literature that's already been done. Our initial issue is just about namespacing, right? So how are we going to name these things? And we want a kind of scalable solution to this, obviously. We want something that's going to work if we do have hundreds of people formalizing hundreds of things. But we could just kind of make something up, then in some random ad hoc way. I think that's kind of unlikely to be scalable. It lead to just general confusion. So we could try and leverage some existing scheme that other people are using. I mean, so obvious thing to do would be to sort of start with a mathematics subject classification that's used by the AMS. So this particular thing for stable commutative category, I mean, the situation's quite simple. That's definitely 55p42. There's nothing else it could be. But other things you might do might not have. You might have kind of primary and secondary subject classifications, and it might all be a bit more ambiguous. And then, but yeah, so you probably don't want to just use these numeric identifiers, but the MSC does have a kind of hierarchical classification with sort of names for different subdivisions. So if you just follow that, then you call it something like algebraic topology, homotopy theory, stable homotopy spectra.lean would be a sort of natural name for this file. But yeah, so it would be worthwhile to kind of analyze a bunch of other kind of new papers and just sort of see whether they fit nicely into a sort of naming convention like this, or whether we have to do some more work. And there's also, you need to, well, we can at least ask ourselves whether these sort of developments ought to be linked to some kind of original reference in the literature, some canonical place where they first appeared. So, I mean, this is kind of, again, a sort of little test case for that kind of question. Unfortunately here, everyone agrees that, the first satisfactory version of this category was defined by Boardman, but he didn't actually publish it. It was mimeograph notes in the Warwick University Library, which is a canonical reference for these. But yeah, and for many years, people would always refer to this book by Frank Adams, which developed this theory, and so you could kind of think about attaching to that, and like everything that's actually been published has a math sign identifier, which so that's a pretty good stable identifier for these kinds of things. But of course, there's a bunch of stuff that's on the archive. I don't know if it's been formally published. That doesn't have math sign identifiers. So that's just kind of the beginnings of questions about how we might refer to the literature. I did kind of, I did hope to sort of get a bit further with this particular question and do some, do some kind of mock-ups of lean code that you might use to deal with this. But unfortunately, as I mentioned to some of you, I destroyed my laptop the other day and bought a new one, and it's created some technical problems which prevented me from finishing these little experiments with lean. So I will stop at this point.
Are there any questions or comments?
Yep.
Why do you think that pull requests are not scalable with Unity? It seems to be scalable for projects like Linux.
Yeah, that's true. I mean, I guess. So you would need to scale. You need to increase the community of reviewers on the same kind of scale that you're increasing the community of submitters, I guess. So I mean, maybe that could happen. But yeah, yeah. I just observe that at the point we are at present, things are not terribly fast. Maybe the numbers could change in such a way that they would become fast.
So I think that part of the problem is that things are not very compartmentalized right now. It's not that you can have one corner, to some degree you can, but it's not like everybody has one corner of expertise and can use all of the rest there. This is more or less an artifact of the MathLab organization. I think we could do a better job at that. It might speed things up, but it's also a matter of balancing the number of people doing that, or contributors, etc. I don't think that it's a possibility going forward.
I find quite amusing the fact that the number of papers published in computer science and mathematics is roughly the same in our time. So just wonder, is there not a typo?
No, no. First, I was wondering about this, and I just Googled it earlier this morning. So I can't claim to have checked it, but yeah, I mean, if you search Google for archive submission statistics, then you will find that there's a nice page that gives you nice pictures, and that's what it shows. It is. Yeah. Yeah, it's an official page, and when I also when I say math, that's mathematics and mathematical physics together. So I don't know what's the split between those two.
Think it matters that your code might rot?
Yeah.
Do you think then that my impression is that when MathLib updates and makes breaking changes, all the reviewers kind of know what happened. People like me that aren't reviewers are just blind to this. And occasionally me and Patrick and Johan notice that the effect on the project is compiling. And they have to kind of figure out why that happened. I think you're right that it would be nice to somehow get instantaneously. Is that possible? You get instantaneously notified?
Well, yeah. I mean, I think it should be possible to configure Travis to do these kinds of things. I would have thought. But
there are ways to set up something like this.
Yeah, I mean,
because my impression is the moment my code breaks, if I just came along and said, "Why did my code break?" I would instantly get told by somebody that just accepted a thing. Oh yeah, something happened. You just fix it up.
Yeah, but of course, there's an issue with that is if like I said, I spent a few months not really being engaged, and so then I come back after a few months and I find that the stuff is broken. Then people have forgotten the PR that broke it.
Anyone got any more? Oh yes.
Michael, you're explaining the I guess. Is there anything you would do differently? Just provide more file.
Yeah, I mean, I think I would invest some more time in trying to think about the TOML files and those kinds of things. But,
So you have this example here where you say that it wouldn't be scalable to just make up your own. And actually, that confuses me. What you're creating here is not a pseudo definition, as you said.
Yeah.
So eventually, hopefully, someone will come along and create the real definition. That's going to require some work anyway.
Yep.
So even if you happen to put it in the same name file, I mean, all that's going to do is cause another problem.
Right.
Like you still have to go and swap out the fake definition that you have with the real one. When you do that, inevitably, it's not going to match exactly. You're going to have to make.
No, he's going to make a beautiful API.
Yeah, I don't know. I mean, I think a bunch of things would happen that we probably can't anticipate in advance. But, you know, suppose I do this and some random other algebraic just sort of wants to do a similar thing. I think it would be helpful if there were kind of reasonably consistent naming conventions so that people could sort of easily find what other people have done and either directly use it or at least sort of mirror it and try and keep things consistent.
Yeah, a quick comment more than a question. So first of all, I think that there are lots of things in your talk that are like very good starting points for discussions on Thursday and Friday.
Okay.
Spend time talking about macro and stuff for them. But on the point of connecting a formal document and an informal document, there are approaches in, well, I know in Isabel and in other systems for sort of doing this, generating PDFs from your formalization, et cetera. And I mean, I think that it would be good to have a more general specification for this kind of thing, not Lean specific, not Isabel specific, because this kind of linking formal and informal documents is great not only for human readers, but also if you're trying to data mine or
Sure, yeah.
machine translation like that. So, it'd be nice to have like a protocol or specification.
Yeah.
And let's thank Neil again.